want to do a quick introduction on AI Camp. We are a global online platform for developers, engineers, and data scientists to learn and practice AI technology, with the mission of make AI available to all developers. AI Camp have grown to over 70,000 tech engineers in the group, have hosted over 300 local tech meetups, workshops, boot camps, large tech conferences, and live stream most of the tech talks globally. We have local study groups in the major cities in the US, a few cities in Europe, India, China, Australia. You can take a look at the website to see our upcoming tech talks, workshops, and crash courses that we offer. So starting this week on March 5th and 7th, 10 a.m. to 12 p.m. Pacific time, we have our online workshop on dimension reduction from modeling to visualization. You can learn about widely used dimension reduction methods such as PSA, ICA, TSME, and UMAP. You can learn how to explore them to reduce dimensionality of your data in Python. We will cover 8 topics in 4 hours live talk, 3 hands-on collabs, and you will have the real-time interaction with the instructor. You can still join in now, even we already started, because all the courses material are available on our website. So going back to our main topic today we are excited to have Taylor, founder of TapLab. Taylor is an educator, technologist, writer, programmer, and all-around a curious human. He holds a bachelor degree in computer science and completed his MBA by counterexample in San Francisco startup scene. He is now focused on technology education, outreach, and policy. So without further ado, let's welcome Taylor to talk about machine learning in databases.
Okay, awesome. Hey, everybody. Thanks for having me. I'll share my screen now with you.
Let me share mine.
Okay, right on. Here we go. So this talk is about machine learning in databases, and specifically about a really interesting paper that was published about 2 years ago by MIT and Google, comparing not just hash tables and B-trees to their new machine learning index strategies, but a few other things. We are only going to talk about hash tables, B-trees, and learn indexes, but I'll send you the link to the paper. It's very, very interesting, provocative stuff. So, just quickly, you saw this picture of me already. My name is Tyler Bettilyon, and I teach computer science and computer programming. I release a lot of open source online material. So at the end of the talk, I'll share some links with you if you want to read some of my other writing or look at some of my other educational materials. But let's get right into it. So this talk is fundamentally about database indexing and new tactics to apply database indexing revealed by the MIT and Google researchers. And indexing is basically a strategy where you have a lot of data. You've got a big old database with 100 million records per table, stuff like this, and you need to be able to look up specific items within those tables quickly. So we use an index for this, and we typically use 2 kinds of indexes, hash tables and B-trees. These are extremely well-studied data structures with interesting and nuanced modifications to each one of them. So I'm going to describe the overarching strategy of both hash tables and B-trees, and then point at some places where you can do further study if you want to, say, implement one of these 2 things from scratch, especially in the context of like a database index. You'll be able to do that. But today, just a high-level overview of those 2 strategies. And then we're going to compare those 2 strategies to the paper I mentioned, what Google and MIT published. That's a link to the paper on Archive Vanity. And then finally, we'll look at some of their results and kind of look towards the future and see how indexes stack up. There are going to be some times when the old school algorithms still have an advantage over the new hot machine learning algorithms, but there's also some very interesting advantages that the machine learning paper describes, even for something as old and well studied as indexing, which I think is pretty cool. Okay, so when I talk about indexing, like I said, what I mean is building a secondary data structure that tells us something about the location of particular samples of data in a larger data store. So in the context of, say, one database table, we might create several different indexes against that individual database table. So, say we have a user table, we might have an index on name and an index on age and an index on sign-up date. And we'll build 3 separate indexes in order to help us query against those fields, help us quickly extract data rather than just kind of looking through all of the rows of our database table. So here's an example. We're going to use this visualization throughout where each of these little blocks represents a single row in a database table. And really, you should imagine that in the context of indexing, there's hundreds of thousands or millions or hundreds of millions of rows. So if I want to do something like ask the question, where is Tim's database record? And I don't know the answer to that question, I don't just have to scan through the entire table, right? These are ordered by basically insertion date. They're packed as tightly as they can be so that the database is, efficiently using the space that's allocated to it. So if I want to find Tim and I don't have an index, I just have to check every single one of these records, go to the name field and say, is this Tim? Which, it's incredibly inefficient if we have a big database table. So an index is a way for us to build a secondary data store, build a different, data structure, B-tree or hash table or a machine learning model, and have that data store tell us only the answer to the question, where within the overarching database is Tim? So I send that query to the index. It tells me, oh, Tim is at memory address 7 relative to the start of this database table. And we can go directly to that record, okay? So, like I said before, indexing is kind of a very straightforward way to trade off computational speed for memory. We build a data store that takes up extra memory in our database, makes our database bigger, but it gives us the added benefit of doing things, specifically lookups, a lot faster. Okay. So there's different things we care about when we talk about indexing. We care about really 5 major performance considerations. So there's 2 important types of queries, individual and range, and we also care about the speed of looking up a particular item from our index, the cost of inserting a new record, both in terms of the amount of data that record's going to take up and in terms of how fast it is to do that actual insertion, as well as the cost of deleting and the total overall size of our data store, of the index. So when I say there's 2 types of queries, really we only care about these 2, a point query and a range query. So a point query, we've already seen an example. We ask, hey, where's Tim's record in this database? And we can go right to it from asking the index. And a lot of times, we want to ask a range query, hey, can I get all of my users who are aged 5 to 12? And we'll more commonly use a B-tree for this type of query. But range could cover anything that has, an ability to be ordered, any data that has a natural sort ordering. We can make a range query out of that. Okay. So like I said, we care how long this takes when we build an index and we want to find where Tim is. The speed of this operation is really important to us in terms of measuring the efficiency of our index. Similarly, if I want to add a new item to my overarching data structure, I don't just need to add it to the database table, but I also need to make a copy of that data and put it into the index. So if we have an index over, the name and the age of all of my users in this database table, then I'll make 2 new records, one for the name index and one for the age index. And I'll have to insert both of those things. So when we talk about the performance of indexes, we care about how costly this operation is. And similarly, if we delete something from the underlying database table, we also need to update the index so that we free that space up for new records later on in time, and so that the index doesn't give us a wrong answer to a question. We don't want to ask the question, hey, where's Tim? And Tim's been deleted from our database, and have the index tell us, oh, go to record 7, that's Tim, when in fact, he doesn't exist anymore. Okay, and finally, we care about the overall size and utilization rate of indexes. One interesting thing about indexes is that in a common hash table implementations, it is extremely regular for only about half of the entries within the overall space that's been allocated to the hash table to contain data about indexed items. And the other half of those spaces are just empty. They're allocated there because we need extra space to avoid hash collisions, which we'll talk about in a second. But both B-trees and hash tables allocate a lot more space than there are items that are actually indexed. And that's an interesting, detriment to the standard algorithms that have been used since the 70s. Okay, and finally, there's one important caveat to this whole thing, and it's a caveat that also impacts the power of the paper that we're talking about, which is indexing is mostly a tool used when we're talking about a ton of data that can't fit in memory, enough data that it has to be stored on the hard drive. So while definitely there are uses for hash tables in-memory hash tables and in-memory B trees, a lot of the most important considerations for indexing happen in hard drive-based data structures. So we frequently optimize these indexes over accessing the hard drive the fewest number of times, rather than just doing the fewest number of operations, because those hard drive accesses are really slow. And the paper, the MIT-Google collaboration, they focused exclusively on in-memory indexes. So there's still some open questions about whether or not this model will continue to be really effective in the context of databases on the hard drive rather than databases in memory. So keep that in mind when you're thinking about this, but it's still very interesting and positive research for certain contexts. Okay, so that's kind of the overarching picture of what's an index. Now I want to talk to you about a hash table. I'm sure many of you already know some of this information, so we'll breeze through it not too quickly. A hash function is the fundamental unit that allows us to build hash tables, and all it does is take some arbitrary data, a key value, throw it through a hash function, which is usually a very efficient operation. It's like 3 XORs. It's very, very fast. And it just returns an integer within some range. We use the modulo operation to bound it to a range, but we take an arbitrary key value and it produces an integer. That's a hash function. When we add a hash table, we take that key value, that arbitrary data, we throw it through the hash function, we take that integer and use it as an index into the secondary data structure, the hash table. And within that hash table, we store at that location the memory address for the underlying data structure, the database table. So that looks like this. If we have Tim, our running example, and we want to know where Tim is in the database table, we throw the value, the key, Tim, through our hash function, say it produces 15, then we look at index 15 in our hash table, and then that record in the hash table will contain the address in the database table where the entirety of Tim's record is. So we first do the hash function, we get 15, we look up index 15 within the hash table, and the hash table tells us where to go in the actual database table. All right? And these are really, really good for individual point-to-point lookups, and they're not as good for range queries. This is because the hash functions are totally agnostic. If we go back up here, we said Tim produced the hash code 15. Inside of nearly all hash functions that are commonly used, there's no reason that the word tin would produce anything close to 15. In fact, it might produce something wildly different, like 0 or 5 million, So if we're doing range queries, hash tables have poor performance because we just have to hash every item that's in that range and go look it up individually. So we'll see B trees are better for this. But the query time is great. It's, constant time to access, constant time to delete, because we just do the hash function, which is fast and constant time, make one memory access to the hash table itself, followed by a memory access to the database table, the underlying database table where the real data we care about is, okay? Deletion and insertion are the same. We just perform the hash function, look it up in the hash table, and then either insert the new record into the place the hash function told us to, or delete the record from that location. Size and utilization, there are some gotchas here, especially when we have a hash collision. So let's say 2 values go through our hash function and produce the same output value. In that case, we have to apply a collision handling strategy, and those collision handling strategies almost always cause us to suffer utilization rates. So this is on the gotcha page. You can look at more of these collision handling strategies. For the paper that we're talking about today, they used chaining, which is a kind of simplistic approach. It's very popular, but it's known to be pretty slow, where as soon as you experience a collision, you just replace the item in your hash table with a linked list of all the items that produce that same hash code. You can look up more linear probing and cuckoo hashing. Linear probing is very popular in language implementations, and cuckoo hashing is a little bit more esoteric, but it has really good utilization rates. Okay, some other gotchas that we don't have to deal with for the Google MIT paper, but that you should be aware of, is that inserts might require us to rebuild the entire hash table. For example, let's say we insert and we're out of space now. We don't have any more memory allocated to the hash table, and we have to add one more item to our underlying database table. Then we have to get new memory and reallocate the entire hash table. So we copy the entire hash table to a new, bigger memory space. Okay, and then we can choose different hash functions. There's like murmur hash and prime modulo strategies, and a few other kinds of interesting hash function strategies that can impact the rate at which we experience collisions. So an ideal hash function will produce, a uniform distribution of values within the space, and some hash functions don't do that. Some hash functions might produce more collisions than a uniform distribution would, okay? So those can impact both the speed and the utilization rates of a hash table. Okay, so that's hash tables. It's very good for point-to-point lookups. The next common indexing strategy is a B-tree. And a B-tree is a lot like a binary search tree. So if you've studied binary search trees, this will feel familiar. But unlike a binary search tree, instead of having every node have just 2 children, every node has often on the order of hundreds of children. So the branching factor of our B trees is very, very big, which means the depth of our B trees is very, very small. But just like a B tree or a binary search tree, if you follow the leftmost pointer all the way down to the bottom of the tree, you will find the smallest or first element in the sorted order of your total data set. And similarly, if you follow the right pointer all the way down, you'll find the last item in your sorted data set. All right, so B trees have, like I said, often hundreds of nodes, but each of the root and internal nodes, as opposed to the leaf node, are basically just subdividing the data into more granular divisions. So at the root, if we're talking about an index over the names in our database table, our root node might have pointers for all the names that start with the letter A, and then all the names that start with the letters B through D, and then another pointer for all the names that start with E through G, kind of like a multi-volume encyclopedia. Okay, and then if we follow the A nodes pointer, all the words that start with A, then we'll find a more subdivided version of A. All the words that start with 2 A's through all the words that start with AB, like from aardvark to abate, whatever. And then similarly, a subdivision for all the words from AC to AD. And then finally, when we get to a leaf node, say we follow this AE through AG node, when we get to a leaf node over here, it'll contain actual words like aeon, afar, afraid, and agriculture. And those actual words will also map to the memory location in the underlying database table that we're interested in. So I'll follow the root node from, let's say I'm looking for the word agriculture. I'll follow the root node to its child for A. I'll follow the first internal node to its child for AE through AG, because agriculture starts with AG. Then when I get to the leaf node, I have to perform a search. It could be, a linear, but more commonly it's a binary search within that leaf node itself for the word agriculture. And when I find that word in the leaf node, that will tell me where to go in the actual underlying database table. Okay. So using a B tree is an iterative process. It looks like this. First we grab the root node. We find out which subdivision within the root node our data resides in by scanning all the entries in that root node. And when we find it, it tells us which node to read next. And, because in databases anyway, this has been highly optimized for hard drive access, and the B tree itself lives in the hard drive. A lot of the time when you're building these B trees, you build the size of the node, not based on how many items are going to be in that particular node, but based on how much data your machine, your computer, fetches from the hard drive at once. So, just like RAM is buffered into your L1, L2, and L3 caches, your hard drive is buffered into RAM. And if your computer grabs, 14K of memory from your hard drive at once and throws that into RAM, it's extremely common for database implementations to optimize for that 14K. So they say, we'll make the size of every node in the B tree 14K, if that's my block size. And we'll see in this paper, they experiment with different block sizes, different B tree node sizes, because they're focused on in-memory node sizes. They have a little more flexibility in changing that number. Okay, so how do B trees stack up? They're really good for range queries because, as you can imagine, all those leaf nodes already contain ordered data. So if I want to fetch all the items from, AA through AB, I just go to that leaf node that contains all those items and return them sequentially because I know that they're all in there. So they're really good for range queries, and they're still pretty good for individual queries. They're not constant time performance, they're logarithmic time performance because we've got a tree with a branching factor of 100. And the depth then is going to be basically log base 100 of n. So we've got really, really shallow trees, but still, it's like 3 to 5 lookups rather than just 2 lookups for the hash table. Okay, so a little bit slower, but still very fast. It's super common to use. Insertion and deletion are similarly log n for the same reason. We just go to the place where we need to delete a record in log n time and then delete that record, or go to the place where the insertion should fit and insert that record. And similarly, size and utilization vary across B trees. It depends a lot on what block size you choose, and we'll see that in one of the tables from the results of the Google MIT collaboration. But we'll see that choosing an appropriate block size can really change the overall utilization rates and therefore the overall size of our B tree. Just like hash tables, there's some gotchas. Okay, so B trees have to be relatively balanced, otherwise the performance won't actually be log n. So that means when we build the B trees, we have to be careful to make sure that we're allocating, appropriately balanced B trees, not just always following the left pointer and putting things on, the left pointer, or we'll end up with a linked list. So this is an implementation detail that can be tricky. There's a lot of interesting algorithmic work to help build the B tree in a balanced way. And similar to hash tables, insertion and deletion might cause expensive either rebalancing operations or expensive split operations. For example, if you're inserting into a leaf node that's already full, doesn't have any more data, you have to split that leaf node into 2 leaf nodes and make an entry in that parent node. And if those cause cascading splits all the way up to the root, then you have to split the root and your tree gets one more depth, which can be potentially problematic, right? Okay, so that's B trees. Now we're going to talk about the learned indexing structures that are competing with these two. So Google and MIT did this very interesting collaboration saying, hey, indexing is something that's been going on for a long, long time, and we want to take some new instruments to bear on it. So the critical insight that they started with is that hash tables and B trees are really just models where you're taking a key value and you're predicting a location in memory. So this is fundamentally just a regression problem, they say. And furthermore, range index are really just cumulative distribution functions. So if you think of estimating the position as taking the result from your model based on the key, and you just multiply it by the number of elements that are in the database table overall, you'll get the estimated position. And so now with this insight, we can start applying any regression model that we'd like to the problem of indexing. There are some important caveats that the researchers start out by informing us, right? If we take some machine learning model, unlike standard indexes, which have been, they must produce the exact location in memory, and that's how indexes have been built. That's their whole purpose. Machine learning models are, probabilistic and approximate. We're not going to get out of any, neural net or, random forest or really any machine learning model. We're very rarely going to get the exact answer that we're looking for. In fact, most of the time we'll say if we did get that for our training data, we'll say, well, maybe we're overfitting, right? But the index has to return the exact location. An approximate location is not enough. if Tim's record is at offset 7 and my machine learning model returns offset 10, that's wrong and it didn't actually help me. So they address this in a pretty straightforward brute force kind of way. Every time we get a new, we perform a round of training and we produce an approximate location in memory, we just make a note of what the actual location in memory was, and we track the overall minimum error, meaning most negative error off by most negative amount, and maximum error off by most positive amount. And then every time we have our machine learning model make a prediction, every time we have it try to tell us where in memory this item of interest is going to be, we just do a table scan or a binary search in between the bounds produced by our guess and the minimum error and our guess and the maximum error. Okay, so that's how they solve the approximation problem. And then they further went on to say, okay, not only can we replace B trees by treating our model as a, something that's predicting to a CDF, doing regression over a CDF, they also observed that we can, instead of replacing the hash table holistically, we can just replace the hash function with a machine learning model that does the same thing the hash function would have done, produce an integer that is the place within the hash table that we should actually store the data. And we can replace that with a machine learning model. And we can still get all the benefits of having a hash table, but we change the way the hash function works by replacing it with a machine learning model. And the big motivation here is that machine learning models, unlike hash functions, can actively take into account the distribution of the data that's being indexed, so we can use the space in the hash table a lot more efficiently. All right. And crucially, one of the things the researchers found is that a single big complex model did not produce accurate last mile results, meaning it would give an approximation with big error bounds. And in order to reduce kind of those error bounds, which is very important for the process of indexing it, if we go back to this slide, making sure the range that we have to scan within is small is really, really important. And so the researchers used a collection of models, and all the results I'm going to show you are the result of having a two-stage model, where there is one model at the very top that predicts within a range of submodels. So each submodel is basically subdivided by the amount of spaces within the database that it's responsible for. So let's say you had a database table with 100,000 indexes. The first model of the second stage might be responsible for predicting between 0 and 10K. And then the second one would be responsible for predicting between 10K plus 1 and 11K. So they subdivide and kind of spread the load of what the machine learning model should predict. So one machine learning model first says, oh, use one of these 100 or so other machine learning models to predict where the value in the actual database table was. And they said that they found this approach to be extremely helpful in increasing the average accuracy of their predictions, getting last mile accuracy closer rather than adding more complexity to try and get closer in one big overarching machine learning model. They opted for some pretty simplistic machine learning models, but cascading them in a hierarchy. Okay. So what the researchers found, super interesting, and let's do some background so we know what's being compared. For each of those models in this recursive structure here, those machine learning models were each fully connected neural networks with at maximum 2 hidden layers and at maximum 128 nodes per hidden layer. They go on in the paper to say they actually had extremely good success with models with 0 hidden layers. So very, very small, fully connected neural nets, okay? And they're comparing their results to some also fairly naive, straightforward implementations of hash tables and B trees, not the most hyper-optimized ones that you'd find in, say, a Postgres implementation. So in this way, they're kind of comparing apples to apples, simple machine learning models compared to the simple versions of indexing structures. And then critically, this is an area where the researchers highlight they need to do more research on this area, but they focused on only indexing strategies where you create the model once and then you never insert to it. You only read from it. And furthermore, they were in-memory indexing structures rather than on hard drive indexing structures. So those are two pretty important caveats, in my opinion, about how effective this is right now. But the results are very promising and lead us to want to do more research on, not read-only indexing structures, but ones where you read and write and, they're updated dynamically. It'll be a harder challenge, certainly, but it's very, very promising. So let's look at this. I'm sorry for the graininess of this image. This is the image they provided in their paper, and this is the resolution that they provided it at. So we're stuck with it. But here's what we're looking at here. We're looking at several different B trees, and the only difference between each of these B tree implementations is the page size, which is how many entries per node there are. Okay, so they chose 128 entries per node as the baseline, and all of these percent differences are related to that B tree's performance. All right. In the learned index column here, you can see that these stage sizes, these relate to at the last level. And again, this is only a two-stage recursive learning model that I described, where, this first one, it says second stage size 10,000. That means each of the bottom level machine learning models is responsible for predicting addresses of size 10,000. And they've chunked up the overall database into individual chunks of size 10,000 and have individual machine learning models predict for 0 to 10,000 or 10,001 to 11,000, 11,001 to 12,000. Okay. And the results are pretty amazing, especially in terms of the size savings. So look at this, the overall size of the B tree for this particular data set. And this particular data set, I should describe that too, is a collection of web requests to a university website. I'm assuming it's MIT's website because they're the ones who published the study, but indexed by time that the query occurred. So you can imagine this is a pretty irregular data set, the distribution is, because class schedules and speakers and holidays and all of this goes into when people are visiting MIT's website. So it's not a super regular kind of distribution, it's a weird distribution. And this is very advantageous for the machine learning models, and you see that in the size savings. So, the page size B tree, the baseline B tree is almost 13 megabytes, whereas these machine learning models, even the biggest one, only takes up 3 megabytes. And curiously, the biggest one is actually, it's faster, but it's not crazy faster than some of these smaller ones. So like at 1.53, you have 47% faster speed, 88% smaller, only 1 meg, 1.5 megs of size. And so you can imagine as we get really, really big data sets, these size savings can be pretty important and pretty powerful, okay? So we can learn something about the distribution of the data and save a lot of size in these machine learning models compared to classic index structures. And when they performed the second kind of thing, where the machine learning model replaces a hash function, but both use the same underlying hash table implementation, just with a different hash function, one that's a machine learning model and one that's a classic random hash, they found that you can significantly reduce the amount of wasted space, significantly reduce the amount of empty slots. And again, sorry for this graininess, but this is what the researchers provided. And you can see, especially on the weblog, that's the data set that I just previously described. You can see the savings on this data set are the most dramatic savings because the machine learning model was able to understand a lot better the distribution of the data and utilize the space of the hash function in a much more efficient way, okay? So we got promising initial results, and what the researchers say about their results and where they want to look for future research is, first, this is the big thing they found, that models are just better at taking into account the distribution of the underlying data, and that means we can almost always increase the utilization rates, right? If we know what the distribution of the data looks like, we can use the hash table or use the B-tree space that would have been used that way much more effectively. Okay. Related to this, and this is a really interesting case for machine learning practitioners, overfitting is sort of the goal in this context because there's no point in indexing over left out data for these types of indexes that the researchers focus on. Create once, read only data. You literally train on all of the data that you ever care about. So you never have to make accurate predictions on any left out data if the context is that you're creating a read-only index. And this actually happens in data warehousing contexts very frequently, where maybe once per day, the index is rebuilt, and that index is used for the whole day. And you don't update the database or the database indexes until the end of the day when you've seen all the new traffic come in and you dump it to your warehouse. So we can overfit really, really well, hyper overfit, and then make accurate predictions for all of the data that we care about because we don't have to generalize to any held out data. Okay. They also found in these contexts that the average error is a lot less important than the total error bounds. And this is part of the reason for their recursive indexing model. This is a little bit unlike other machine learning, use cases where really we don't care about getting close on every single one because we're always going to do some kind of table scan within the error bounds in order to find the exact location within memory. So getting those error bounds really small is much more important than getting the average error really small. Okay, second to last finding is that we have some really interesting properties at scale, and you really saw this in the B-tree size differences. With a standard index, every time I insert something into that index, the size of my index has to grow by 1 unit because I have to make a record in the B tree and I have to make sure it's findable in all the internal nodes and I have to make an entry in the leaf node. Or in the hash table, I have to reserve some space for that entry in the hash table. But because machine learning models, and especially fully connected neural nets, have an enormous amount of complexity just built in, even to small models, it's not clear at all that they have to scale up that much in size as the data grows because they already have enough complexity to produce, a relatively precise value between 0 and 1, a relatively precise regression value. So as we start to index more and more and more data, machine learning models are a way to not scale up the size of our indexes as we continue to scale up the size of our data. Okay, and finally, this was a really interesting thing. I'm glad they pointed this out because I might not have thought of it, is machine learning is taking account of new hardware. Machine learning workloads are drivers of advancements in GPUs and TPUs and all kinds of new hardware advances. And at the same time, classical indexing structures have been optimized over situations where we were using classical CPUs. Moore's law is either dead or dying, depending on who you ask. So CPUs really aren't going to get much faster, which means we won't be able to take advantage of hardware speedups on these classical indexing structures because they're not well suited to parallelization and they're not well suited to, the kind of workloads that are driving the current breed of hardware advancements. So it might be the case that without changing anything about any of these indexing strategies, machine learning strategies will just become faster because we get better hardware. Okay. And then one area that they pointed to, but didn't do any research on themselves, is machine learning models, because of their good performance with multidimensional data and highly complex data, they provide an opportunity that classical indexes never did really provide, which is the ability to index over multiple dimensions at once and still provide relatively good performance.